Yeah, if you remember, do you remember three different regions of that MOSFETs operates, like accumulation region, inversion region, and depletion region, these three regions? So, uh, Let me actually remind you first that here we have a metal layer, and one is oxide layer, and then we have a semiconductor layer here. So, when we actually apply a negative voltage at the metal layer, what happens? So since this is a p-type semiconductor, we have abundance of holes, right? We have a lot of holes in this p-type semiconductor. So when we apply a positive voltage here, when we apply a negative voltage here, what happens? Uh, the negative voltage actually attracts all the holes from the substrate, and those holes actually accumulate in these regions, right? That's why it is actually called accumulation region. Uh, I don't know if the guys behind can see my screen clearly. So this is the accumulation region actually. So what happens is a lot of holes actually gather here. Uh, if we look at the charge distribution in the right figure here, uh, here in the right figure, if you look at the charge distribution, then you will see that negative charge in this region and positive charge in this region. Why? Because we are applying a negative voltage at the gate terminal, and due to this, positive holes are attracted here, right? So think about it. If we increase the negative voltage in the metal, what will happen? The hole will always also increase, right? Hole will also increase. So if you remember, like what is the capacitance actually? So if you remember, capacitance is basically nothing but the change of charge with the change of voltage. So think about it. We have a metallic region. We are changing the voltage, and with respect to that, the charge is also changing, right? So there is a capacitance. And what is this capacitance actually? This capacitance is basically the oxide capacitance. Uh, so we have an oxide layer that separates the semiconductor from the metal, right? So when you apply voltage, there is a negative voltage, there is an accumulation. And uh, let's actually apply a positive voltage now. So actually, let me draw it more clearly here. So we have a metal here, an oxide layer here, and a semiconductor here, right? So what is this semiconductor? This is P plus semiconductor. Now, uh, in the uh, depletion layer, if we apply a positive voltage here, if we connect it with a positive voltage or positive battery, what will happen? The positive voltage will repel, right? Positive repels positive, right? So we have a lot of holes in the p-type semiconductors. So when we apply a positive voltage here, what will happen? This positive voltage actually repels the holes from here, and these holes gets deflected, right? And uh, when an atom loses a hole, what this becomes? Can anyone tell me? So let's say we have an atom, it lost a hole. What will happen? We can think about it receiving an electron, right? Receiving an electron. So if something loses an hole or receives an electron, what happens? It becomes a negatively charged ions, right? That's what a depletion region is. If you remember, Dr. Aziz discussed in previous classes, if holes are removed from an atom, we have negatively charged, negatively charged region here. So if we look at the band diagram, you can see that the band is now bending in the opposite direction when we apply the negative voltage, right? Because now more and more holes are getting diffracted. And let's look at the band diagram here. So if you have a intrinsic material, the Fermi level is just at the middle, right, of the conduction and valence band. But if you have a p-type material, the Fermi level actually moves towards the valence band. So right beneath the oxide layer, we have more negative charge. This is not a p-type material, that much of p-type material anymore. So now the band will bend in such a way that Fermi level actually moves away from the conduction band. If you see here, the Fermi level is like this, and the band kind of shifted, the valence band kind of shifted from the Fermi level, because we are making this region a little bit n-type, not entirely n-type here. But when we apply a large positive voltage, what will happen? The band actually bends so much. Let me actually draw it here. So when you have a large positive voltage, so let's say we have a p-type material, which is like this. We have intrinsic Fermi level here. We have a conduction band. We have valence band here, and this is the Fermi level of a p-type material. Now, what happens if we make it a little bit n-type? So the Fermi level moves away from the valence band, right, to above. Now, if you connect these two, what will happen? The band will actually bend this way, right? The band will actually bend this way. So you see the Fermi level was closer to the valence band. Now it moved away from the valence band, right? Now apply a more positive voltage, a larger positive voltage. What will happen? The band bending will be so much that the Fermi level will be much, much closer to the conduction band. So we will call it the inversion. Why this is called an inversion? Because the Fermi level is so close to the conduction band right now, it can be assumed like a n-type material now here. So we will call it an inversion. So we have now three different regions, right? One is accumulation, and then there is depletion, and there is inversion. Let me actually clarify it a little bit. So do you remember what is depletion? Depletion, what does it mean actually? Can anyone tell me what is depletion is? So depletion is basically nothing, a region where actually atoms lost some electrons or holes, right? These are not free charge. A depletion region doesn't have any free charge. A depletion region is a region where we have positive or negative ions of atoms, right? There are no free charge. Not free electrons, no free holes. So in the depletion region here, when we apply a positive voltage, you see we have a depletion region, but we do not have any free carrier. We do not have any free electrons or holes. But when we apply a very, very large positive voltage, what will happen? It is so large, the voltage is so large that now it can actually attract the minority carrier electrons inside the substrate, right? So yeah, we know that a p-type substrate has holes, majority holes, but it also have minority electrons, right? Not much, but a little bit. So these electrons are now get attracted when we apply a large positive voltage. This is the region. You see a narrow region here. This is the region which describes that we are actually now attracting free electrons here. And now it has become an n-type material. This narrow region has become an n-type material. So we will call this an inversion. So if we summarize this, we can actually think of three different regions. When we apply a negative voltage at the gate, we can say that this is an accumulation region. When we apply a small positive voltage, we can think of it as a depletion region, but not n-type region here. But we have to apply a very large positive voltage to make it a inversion region. And when inversion region is there, we can see that the region just below the oxide layer becomes what? N-type. And a lot of electrons gather, right? A lot of electrons gather. So this, how can we actually determine the capacitance of a MOSFET? So think about it. I have just previously mentioned capacitance is not just the charge. If I tell you measure the capacitance, capacitance is not basically the charge. Capacitance is the change of charge. So for example, you have a device, you change the voltage a little bit, you measure the charge difference a little bit. Now divide these two things. So you have a MOSFET, let's say. You have a MOSFET device, you have source, you have drain, right? Now you're applying a gate voltage. Now what will you do? You change the gate voltage a little bit, like del V. How the charge the overall MOSFET del Q becomes. Then you just take the divide the change of charge by the change of voltage. So if I have a lot of charge, but charge is not changing, for example, I have charge, but they are fixed. Do I have any capacitance? Think about it. Anyone? So if I have a fixed charge, let's say here, just hypothetical case, let's say I have a lot of charge here. I'm changing the voltage here, but I see that the charges are not changing. It's not increasing, it's not decreasing. It remained the same somehow. This is a hypothetical case. Is there a capacitance then? No, there is no capacitance, because capacitance is measured by the change of charge by the change of voltage. So remember that, because in the next slides, you need to actually clearly understand why the capacitance is changing or not changing, why it is remain constant, and like that. So let me draw it in some other slide. So actually, let me draw it in this way. Think about the accumulation region. So in the accumulation region, we have something like this. So this is the metal part, this is the oxide part, this is the semiconductor part. So do you remember what kind of voltage did you apply for the accumulation region? Negative voltage, right? We are applying negative voltage at the accumulation region. So our metal will have, if you go back to the slide here, you see, I don't think you can clearly see, so let me draw it actually. So we have negative charge here. Okay, negative charge. So for this negative charge, there are a lot of holes gathering here, right? So we have positive charge here. Now, if we change the negative voltage, say we are changing it this much, this is also changing, right? This also changes. So let me think about this way. So if we change it, this also changes. If we take the change of charge and divide it by the change of voltage, we will get the capacitance during the accumulation region, right? Think about it. So the charge here is balanced by the charge here, right? Because if whatever negative charge we are actually gathering here, the positive charge, equal positive charge will be gathering here as well. So these will balance each other, right? And this capacitance is basically nothing but the oxide capacitance. Do you remember the parallel plate capacitor? So what is a parallel plate capacitor? In a parallel plate capacitor, we basically have a two plates. One plate has like positive charge accumulated, and there is negative charge divided by a oxide layer or insulating layer, right? So this is just like a parallel plate capacitor in the accumulation region. And let me ask you something. If I increase the voltage, will the capacitor change? Anyone? So think about it. If I increase the voltage, the del Q will increase, but we are also increasing the del V, right? So these are kind of balanced. So we will have a constant capacitance here, and which is basically nothing but the oxide capacitance. And if you remember, the formula of oxide capacitance is, if you remember the capacitance of a parallel plate capacitor, which is basically epsilon A by D. But here, the COA, this is the capacitance usually in MOSFET or this kind of transistors, the per unit area capacitance is described. So there is no A. You see, for COX, we have epsilon A by D. So there is no A here. For oxide capacitance, we have epsilon OX by TOX. So let's go back to the okay. Now let's go to the um, now let's go to the depletion region. So think about it. If we now give a positive voltage, the holes are repelled from this region, right? And since holes are getting repelled, we are getting a depletion region here. And if we increase the voltage here, oh, okay. So if we apply a positive voltage, a small positive voltage, I'm repeating again, a small positive voltage. So we have, uh, holes are getting repelled from just beneath the oxide. So what happens is we have a depletion region. These are not free electrons. These are like uh, depletion region. If you remember, a depletion region is basically ionized atoms, right? Ionized atoms. So if we apply a negative voltage, we have so, so here, if let's say we have a metal region, oxide region, and semiconductor region. If we apply positive voltage here, what will happen? The holes are getting deflected here. So if any atom loses holes, what will happen? They become negatively charged, right? So, but if we now increase the voltage, if we now increase the positive voltage here, what happens? The depletion region actually gets increased this in this direction. Okay. So because the charge has to be balanced, right? As I have said, the charge has to be balanced. But at one point, at a large positive voltage, uh, free electrons, minority carrier electrons begins to gather at this here. Now, when we are at the inversion region, when we are the third case, in this case, if we increase the positive voltage, the the accumulated minority carrier increases. The depletion region no longer increases for the balancing. So what, let me actually draw it. Okay, so when we have depletion region here, so this is defines as positive, this is negative, right? I am in if it is above the y-axis, uh, it says that we have positive charge and here it is negative charge. This is metal region, this is oxide region, this is the semiconductor region. So now if we apply a positive voltage across the metal, then we have a depletion region. Now, if we increase the positive voltage a little bit, the depletion region will increase a little bit. If we increase the positive voltage a little bit more, the depletion region will increase a little bit more. But at one point, we will reach a particular voltage, which is known as the threshold voltage. What will happen in that case is now the voltage is so strong that we can attract the minority carrier electrons from the substrate to the edge of the oxide here. Now, the minority carrier electrons begins to gather here. See, this particular point is known as this particular region is known as the inversion region. So in an inversion region is not a depletion region. Inversion region is what? Inversion is basically the accumulation of electrons. And then the transistor will actually turn on. And this particular voltage is known as the threshold voltage, PTH. Okay. And when we were in the depletion region, when we were actually in the depletion region, then if we increase the charge, if we increase the metal voltage or gate voltage, the depletion region was increasing. Now, since we have an accumulation instead, now if we increase the voltage even more, the depletion region will not increase. The depletion region will remain the same, and we will have a like much higher, inversion region. Now the depletion region will not increase anymore, and this is known as the inversion. So, in our target actually is to determine how the capacitance of the MOSFET changes in these three different regions. In how capacitor changes in accumulation region, in depletion region, and in inversion region. So please feel free to stop me if you have any question or something. I know it's tough from behind to see, So I'm trying to draw these stuffs to make things clear. Do you guys have any question? Yeah, sure. Yeah. Yeah, that's an excellent question, actually. Yes. So think about it. You have a parallel plate capacitor. You can think of it as a parallel plate capacitor. So you are just applying different voltage. Like you are increasing more voltage, more charge are accumulated. So if you look at the formula of parallel plate capacitor, it depends on epsilon A by D. Like the dimension of the parallel plate capacitors, their distance, and epsilon, which is basically the material parameters. So it doesn't depend on voltage. So even if you increase the voltage, a parallel plate capacitor's capacitance is fixed. If you just search, okay, what is the capacitance of this capacitor? It's like something farad. It doesn't depend on any voltage. That's what the capacitor is for a MOSFET when the MOSFET is in accumulation region. Okay, because if we increase the voltage, this increase, but the capacitance remains the same, because capacitance is basically determined by del Q by del V. Now let's look at the capacitor versus voltage characteristics of a MOSFET. So I know this actually should look overwhelming because you will find it tough to understand at beginning. But think about it. This x-axis is basically what? Gate voltage. Okay. And this is 0 gate voltage, and this is negative. This is positive. Okay. Can you guys see the screen clearly? So this is basically 0 axis. This is negative gate voltage. This is positive gate voltage. So think about it. If we apply negative gate voltage, what region the MOSFET is in? Accumulation region, right? And think about it. In the accumulation region, the oxide capacitance, the MOSFET capacitance is constant. Do you see it? This is in the accumulation region. But when it goes to the depletion region, it doesn't remain the same, and I will explain why. But let's look at the strong inversion region first. Why at the strong inversion region, when we apply very, very positive voltage, why the capacitance also remains constant? So let's this is inversion region. I'm talking about inversion region when we apply a very, very positive voltage. Okay. So when we apply a positive voltage, like in the metal layer, we are basically gathering positive charge. And in the semiconductor layer, we have a depletion region and we have accumulation of electrons, right? Now, if we increase the charge here, this will increase the gathered electron here as well, right? Do you guys get it? So if we increase the metallic positive voltage, like metal positive voltage, gate positive voltage, the accumulated electron here will also increase. So this will balance out eventually. Okay. So for the same reason, here you see that at strong inversion, it is constant, like in the accumulation region. But interesting stuffs happens in between when it is neither inversion, strong inversion, not accumulation. So what happens actually? Think about it. So let's put it this way. So when we applied very small positive voltage, what really happened? Did we have any inversion? Did we have any free electrons? Remember, when we applied a small positive voltage, small, we only had a depletion layer, right? This is the depletion region. I'm talking about depletion region. Are you guys with me? So now, when we have a depletion region, now what is happening actually in terms of if we increase the voltage here, now the charge is also increasing here, but the depletion region thickness is increasing, right? The depletion region's thickness is increasing. So think about it. The capacitor of a parallel plate capacitor is basically epsilon A by D. Okay. So if D increases, capacitance decreases, right? Think about it. We are having a thicker depletion region. Not only that, at the beginning of the inversion, so you can think of it this way. We have two capacitance actually. Do you remember the series parallel combinations of capacitors and resistors? So if we have two resistors in series, what happens? Like I have a 5 ohms, I have another 10 ohms. What's the total resistance? 15 ohms. But let's say I have a 5 farad and 10 farad. What's the equivalent capacitance? It's not 15 farad, right? It's something different. It's 1 by 5 plus 1 by 15, right? Sorry, is equal to 1 by C. It's actually lower than 5. If you calculate it, it's something like 5 into 15, 5 plus 15, what happens? Like something 3 point something, 3.75 something, okay? I'm not exactly sure, but something like that. So what happens when we actually connect two capacitance in series? The capacitance get decreased, right? Get decreased. That's what actually is happening here. So when we cross the flat band voltage, if you remember the flat band voltage is the voltage that is required for the band to be flat, right? Ideally, it should be zero, but it is not zero because we have some trapped charge, right? Dr. Aziz has already discussed. When we cross the flat band voltage, we actually have two different capacitance here. Why? Why do we have two different capacitance? Because think about it. We have metal, we have oxide, we have semiconductor. What is this semiconductor? P plus semiconductor, right? We have a lot of positive charge holes. Not positive charge holes. We can think about it like holes, a lot of holes. But when we apply positive charge here, what happens? We have positive charge in the metal layer here. We have negative charge ions here. Also, we have positive charge holes here, right? So do we have one single capacitance here? No. we have two capacitance. Now, one is the oxide capacitance and another one is the depletion layer capacitance. Because there is a separation of charge here as well. One is the negative charge and there is holes, right? So we have two different capacitance. And if we think about it, one is oxide capacitance and another one is the depletion by space SD capacitor. It's called depletion surface density, something like that. So if there is two capacitor in series, what happens? We can call the total capacitance is 1 by COX plus 1 by CSD, right? So the total capacitance begins to decrease, right? That's what actually happens here. If you see, since in this region, let me actually. So in this region, we are dealing with two capacitor, right? Two capacitor. One is the oxide capacitor and another one is the depletion capacitor, CSD. And I have already told the CSD is actually what? Decreasing because of epsilon A by D effect. So the overall capacitance is actually decreasing in this region. So we are so far clear about three capacitor. Why the capacitor is constant in the accumulation region? Why the capacitor is constant in the strong inversion region? And why the capacitor actually decreases in the depletion region? Are you guys with me so far? So there is a point, minimum point at which the capacitance actually goes to the minimum value. This is the threshold voltage. And when the voltage actually reaches the threshold voltage, the capacitor is at its minimum value. Okay. And we can actually calculate it. From this point on, the capacitor actually catches up with oxide capacitance. Okay. Because the depletion region capacitance does not contribute much and the capacitor begins to increase. So here in the figure, you can actually see two different characteristics. One is for NMOS and one is for PMOS. So as you can see, if you know the capacitor of NMOS, you can just mirror it, right? For the PMOS. Because think about it, for the PMOS, what do we need for the inversion? Negative voltage, right? So for the high positive voltage or the positive voltage, we have accumulation layer, just like the accumulation layer in NMOS for the negative voltage. Then when we apply a small negative voltage, we have a what? Depletion layer, the depletion region. And then when we apply a large negative voltage, we have a inversion. So it is basically just the symmetric arrangement like an NMOS. So now, as I have discussed, like how do we typically measure this capacitor and voltage characteristics? We actually measure the change of charge by change of voltage. This particular graph, so I will discuss now for different how actually we measure things. So if I actually ask you, actually find this graph in your lab, what will you do? You will apply different voltages, right? Different voltage and measure the capacitor. How will you measure the capacitor? You will measure the change of charge, right? Think about it. So now, so think about it. You have a capacitor. You are trying to measure the capacitance. What will you do? you will apply voltage, right? So if you apply 10 volt and gets 10 coulomb charge, what is the capacitance? 1, right? No, actually, this is not true. This is not true because I have just mentioned that capacitance is not Q by V for here. It is del Q by del V. Remember. So if you have, let's say, if I ask you what is the capacitance of this capacitor at 10 volt, what will you do? You keep it at 10 volt and change it a little bit, right? Change it, let's say 0.1 volt. And uh, when you have a 10 volt voltage across it, if you have, let's say, 10 coulomb, if you increase this by 10.1, then you have 15 coulomb. So the voltage change is 0.1 volt and the charge change is 5 coulomb. So del Q by del V, what does it become? 5 by 0.1, which is 50 farad, right? I'm just giving you an example. So you just not only apply a DC voltage. If you just apply a DC voltage, it will not work. You apply a DC voltage and on top of it, you apply a AC voltage to see how the charge actually varies. So let me actually draw a graph so that you understand it a little bit better. So you basically apply something like this. If you want a C by V graph, you basically apply, increase the DC voltage. You also apply what? A little bit AC voltage. So you can measure the change of charge with it. So basically, you are applying both. And that's how you know at particular what voltage, what is the capacitance. Are you guys with me so far? So there is a problem with it actually. If you have low frequency AC voltage, that is okay. What is basically low frequency means? Low frequency AC voltage, what does it typically mean? The variation is slow, right? If you have low frequency, your variation is slow, like this, with respect to time. But if you have high frequency, it's like this. You are changing the voltage very rapidly. So there is a problem when we actually try to measure the capacitance with high frequency. That's actually what this graph actually describes. You see this point? For low frequency, we get the exact CV graph as we just discussed. But for high frequency, we don't get the exact graph. Why? Because at high frequency, think about it, we are applying positive voltage and applying very rapid change of positive voltage. So think about it. Why do we have inversion in the first place? Why do we get an inversion layer? Inversion layer is basically nothing, the accumulation of minority carrier electrons. So we have a p-type substrate here, right? For this reason, we have a p-type semiconductor. And what do we have in a p-type semiconductor? Holes or electrons? Mainly holes, right? A lot of holes. But minority carrier electrons are also there. And these minority carrier electrons accumulate at the inversion layer, right? When we apply very positive voltage. But do we have a lot of minority carrier? No. That's why they are called minority carrier, right? If we apply a very rapid positive voltage increase, there is no enough minority carrier that can come. They take time because there is not abundance of minority carrier there. So because and there is two things, these notes, please, Dr. Aziz has prepared these notes. If you just look at these notes, there are two sources of electrons that form the inversion layer here. Two sources. One is basically the generation. So electron basically generates from, like, they gets evicted from another atoms. Okay. And another one is basically one second, diffusion. So are you guys familiar with diffusion? So diffusion is something that when any particle travels from one area to another area where it is not present, So if you have a open smoke, like anything, the fragrance actually spreads throughout the room. How? Because the particles actually moves to the place where it is not present, right? That's what diffusion is. And diffusion is a slow process. Whenever you see diffusion in MOSFET, in anything, diffusion is basically a slow process. So electrons actually gather in the inversion layer by two different sources I have mentioned. One is generation and another one is diffusion. And both of these processes are very slow. So when we apply a very rapid change of AC voltage, very rapid change, think about it, that they don't get enough time to come to the inversion layer and increase, the charge here. They don't get enough time because it's too slow. That's why we don't get, this graph for the high frequency. For the high frequency, the graph is like this, right? And there is one thing that I should tell you. Dr. Aziz will discuss in the next class. Probably we don't have enough time today. So there are two kind of device that we are actually thinking or envisioning here. One is MOSFET and another one is MOSCAP, MOS capacitor. So if we have a MOSFET, actually high frequency is not a problem until we actually talk about terahertz. So MOSFET actually can withstand up to a very high frequency, like hundreds of megahertz, maybe. Don't quote me on that, but something like that. But if we have a MOSCAP, then for high frequency, we actually do not get this graph, like this graph. It is this graph. Instead we get something like this. Okay. So are you guys with me so far, or do you have any question? Please feel free to ask me. Are you good? So I think I will wrap it up here today because lost so much time fixing and stuffs. So hopefully in the next class you will uh, learn the rest of the slides while Dr. Aziz will discuss, or we will probably upload a better version of the video in the Canvas for your convenience. Thank you.